In this video we're going to look at degrees of freedom. So let's say for example you wanted to represent a particle in 3D space. Then we could do that with a coordinate system. So we take some arbitrary point here, which we'll call the origin, and this point here has to be mapped relative to that origin. Now we can do that in terms of our coordinate system. So we could have our x coordinate, we can have a y coordinate, and we can have a z coordinate. So there's nothing new in that, that's simple geometry. Now we also say that each coordinate axis here provides the particle with a degree of freedom. And a common sense look at that is to think about the movement of the particle. So the particle can move in the x direction, so that's 1 degree of freedom. It can move in the y direction, that's a 2nd degree of freedom, and the z direction, and that's a 3rd degree of freedom. Now let's say for example we didn't just have one particle here. Let's say we had 2 particles. That would mean that each of the particles would be able to move in the x, y and z directions. So particle 1 will have 3 degrees of freedom and particle 2 will have 3 degrees of freedom. Now let's say for example we extend that up to a number of particles, say p, then the total degrees of freedom is going to be 3 times p. So for example, if you have 10 particles, each of them have got 3 degrees of freedom, the total system is therefore going to have 3 times 10, which is 30 degrees of freedom. So we're going to have 3p degrees of freedom. Now we're going to introduce another idea here, which is of constraints. Now, the number of constraints that you add in is going to decrease the number of degrees of freedom. Now, a typical example that we can look at that is if we have 2 particles, but they're actually joined together. So the distance between, say, the first particle, which has got coordinates x1, y1, z1, and the second particle that's got x2, y2, z2, and if the distance is kept the same between the 2 particles, irrespective of the particle's position, then the distance is going to be given by this equation here. So this really is just telling us the distance between the particles at x1, y1, z1 and the particles at x2, y2, z2 is a constant value, which is a value of L. So the idea here is that we can find, say for example, a value x1 in this equation if we're given the values of our y1, z1, y2, z2 and x2. So it means that if we can create an equation which joins together the coordinate system such that we can find one value given the value of all the others, then that means that we're going to have 1 less degree of freedom. Now you can see that here in this example, and if you think about 2 points joined together, in effect the 2 points are connected by a rod, and you can see that as that system moves around about, as the system moves, then each of the particles at one end of the rod is going to be, their movement is going to be controlled or fixed. So we're going to lose a degree of freedom. That is that one particle cannot move completely independently of the other particle. So what we can say is that this system then is going to have 3p minus 1 independent coordinates. Or in effect it has got 3p minus 1 degrees of freedom. So in general, if we've got p particles and we've got r constraints, so in that instance there the constraint was this equation here, then we're going to have 3p minus r degrees of freedom, and we're going to need 3p minus r coordinates in order to describe the system. Now, one other thing we're going to talk about here, but we'll cover it more fully in the next video, is the idea of generalized coordinates and generalized velocities. This point here can be represented in a Cartesian coordinate system as an x, a y and a z component, and that tells us this point here relative to this origin. But we could represent the point also in polar coordinates or cylindrical coordinates. So what we do is we introduce another idea, and that's the idea of a generalized coordinate system. So in the generalized coordinate system, we define the generalized coordinates as qi, and we'll define the generalized velocities as qi dot. But we'll talk more about that in the next video. So we've seen in the last slide that we can create constraints, and constraints are nothing other than an equation which involves the coordinates in that particular coordinate system that you happen to be using. And for each equation that we can create, we're going to reduce the degrees of freedom by 1. So let's look at an example here. So let's say, for example, we had a sphere, and the sphere exists in 3-dimensional space. So this sphere here then is going to have 6 degrees of freedom, and we can see that because if we were to look at the centre of mass of this sphere, so the centre of mass of the sphere obviously is just the centre of the sphere, so we'd have this point here. Now this point is going to be defined by an x, a y and a z, so that's going to be 3 degrees of freedom. But if you were to put a little dot on the surface of this sphere, in order to define that dot relative to this point here, you're still going to have the 3 angles. So in order to get that, you're going to have 3 angles, say theta and phi and say an angle of psi, in order to work out the exact position of a dot on the surface of this sphere. Now if you're unsure about that, I suggest you get a tennis ball and you put a little dot on it, and then you sit it at the corner of a table, and then move the tennis ball to another point in space, so you'll have an x, a y and a z, and then turn the tennis ball round in each of the 3 axes of the tennis ball, and you'll see you're going to have 3 different angles to represent that movement. So all in all, we're going to have 6 degrees of freedom. That is 6 axes. And also we could say now we're going to have 6 generalized coordinates. We're going to have 3 to fix the centre of the mass and 3 to fix the orientation of this body. Finally, let's look at this last example here. Let's say we have got a rigid body. Now a rigid body is just made up of p particles, so it's a number of particles, and the distance between each particle remains the same. So it means that we can think about this rigid body as having these little blue dots. So these are in effect the particles, and we're going to have the rods which join each of the particles together. So you can think about the blue dots here as the p particles, and you can think about the yellow lines here as forming the constraints. So we can call the constraint r. Now we've drawn them as straight lines here because we're assuming that the distance between each of these points always remains fixed, irrespective of how the body moves. That's why we call it a rigid body. So we've seen for a rigid body up here that we're going to have 6 degrees of freedom, 3 for the position and 3 for the orientation. So we can say then that the number of degrees of freedom 6 is going to equal 3p minus r. Or equivalently, we could say that r is equal to 3p minus 6. So remember, r is just the number of constraints and p is the number of particles. And the value of 6 here gives us the number of degrees of freedom for the system. So the question here we have then is, how many ways can we join P particles together with R rods? So it turns out the equation is this equation here, and we'll go through and we'll have a look at that just now. So let's say, for example, we've got 2 particles. Then we're going to join them together with just 1 rod. If we have 3 particles, we can join them together with 3 rods. If we have 4 particles, we can join them together with 6 rods. That's 1, 2, 3, 4, and the diagonals here, which is 6. And if we had 5 particles, which I've shown here, we can connect them together with 10 rods. So you check for yourself. You can see that if we take this example here of 4 particles, we're going to have 4 minus 1, which is 3, times 4 is 12. 12 divided by 2 gives a value of 6. So this equation tells us how many different ways we can connect together P particles with R rods, and the R rods represent our constraints, and each rod that we add adds in 1 more constraint, and it decreases the degrees of freedom by a value of 1. But that doesn't quite add up whenever we look at the example we had above. So let's say, for example, we had the P was equal to 5. Then from above, we're going to have our R is equal to 3P minus 6. So R, which is our degrees of freedom, is going to be, R, which is our constraint, is going to equal 3P minus 6. So in this case, P is equal to 5. So 3 times 5 is 15, minus 6 is 9. So we are saying that the constraints here are going to be 9. But whenever we put our value of 5 into this equation here, we get our constraints are actually 10. So there's a difference here of 1. Now, in this instance here, what we would say is if we were to follow this equation here, which gives us the maximum number of rods or constraints, then we would say this system would be over stiff. But if we were to follow the 3P minus R, we would say it would be simply stiff. So what we could do is we could actually get away with removing one of these rods, and this system would still be a stiff system. But if we were to maintain the entire number of rods, we would say the system would be over stiff. So that's just a little introduction of the ideas of degrees of freedom, and we can see how they relate to our coordinate system, and also how they relate to our generalized coordinates. Now, we've not talked much about the generalized coordinates, but we'll go and we'll look at that in the next video. So thank you for listening. I'll get you on the next video. Goodbye.